So now we're continuing 4-1, and we're talking about vertical and horizontal asymptotes and how do we find those. So again, looking at this nomenclature, which can be a little confusing, let's just review this. As f of x is approaching negative infinity, so that means as the y, remember, that's the y, is going to negative infinity as x is approaching negative 0. So if you're going to negative infinity in the y value, that means you must be coming this direction from x to 0 from the negative side. That's why there's a negative here. And then this one says f of x approaches positive infinity as x approaches 0 from the positive side. That's why they have that here. So this is a vertical asymptote going along here. Usually it's depicted with a dashed line. The in behavior, so in this situation, if I go back, let me erase this. If we are approaching 0, so let's see, look, as f of x is approaching 0, whoops. So as this is approaching 0 here, then x is approaching negative infinity. And as it's approaching 0 right here, x is approaching positive infinity. That's what these two mean. Okay, so the definition of a vertical and horizontal asymptote, it's really, the way I look at it, it is a force field. I like science fiction, so that's how I think of it. It's a force field that you cannot cross. It will bounce you back if you try to cross it. So that's what an asymptote is. So it is a line that is vertical, and what happens is f of x will either approach infinity or negative infinity from left or right. And then for the horizontal asymptote, then f of x, or the y value, will approach b as x is approaching infinity or negative infinity. So let's look at some examples here. We have both a vertical and a horizontal asymptote here. This one is at x equals negative 1, and this is y equals 2. So your horizontal asymptote is what's in the horizon, the flat part, and the vertical is going up and down. This one has a horizontal asymptote at x equals 0. And this one has a vertical asymptote at x equals 1 and at y equals 0. There is a way that you can look at the formula or the equation of the graph to figure out where the asymptotes are going to be. So let's look at a basic parent function here of a rational function. This again is 1 over x. It is a hyperbola, and we know that there is a vertical asymptote because we are going to set every factor of the denominator equal to 0. Here we only have one factor, and it's x. And so x equals 0 is our one asymptote here that's vertical. Now, if you want to know why this is a horizontal asymptote here, it has to do with the degree on the top and the bottom. This degree, there's no x here, so the degree on the top is 0. The degree on the bottom is 1. Because the bottom degree is larger than the top degree, we know that it's going to have a horizontal asymptote at 0. There are rules that I want to show you for this, and here they are. This is something you would want to write down in your notes because eventually you'll need to have it memorized, but it's important. So, for your vertical asymptotes, you need to factor the bottom, the denominator. and set each factor equal to 0. Solve for those. You may have more than one vertical asymptote. Horizontal asymptotes have everything to do with the degrees. Again, here's N, here's M. If the degree on the top is smaller than the bottom, you will always have a horizontal asymptote at y equals 0. So I would write this in your notes. When N is smaller than M, you have a horizontal asymptote at y equals 0. And if you want to write this part of the equation down in your notes, that would be good. This other stuff here doesn't matter with this particular part of figuring out the asymptotes. If N is equal to M, then we're going to take these two coefficients here and we're going to turn them right into a fraction. It's A over B. That is where the horizontal asymptote is going to be. So whatever it is simplified, it will be, like say it's 4 over 2, then it will be at 2. Because 4 divided by 2 is 2. Okay, part C. If N is larger than M, if the top is larger than M, it has no horizontal asymptote. It is called a slant. It does have an asymptote, but it's not horizontal, and it's called a slant. Write that word down there. We might cover this in the next section. But if you want to find out what the equation of the slant is, really you have to divide the top completely by the bottom using long division. All right, so let's talk about these two examples. The first one, if you notice that if I were to set this equal to 0, there is nothing in here. I could put any number in for x, and it will always be a positive number. There is nothing that would make this denominator a 0. So I can say there is no vertical asymptote here. Okay? But this degree is equal to 1. This degree is equal to 2. Notice that 1, which is the top, is smaller than the bottom, which is 2. And if we go back to our little chart here, if the top is smaller than the bottom, we know we have a line at y equals 0. So we have a horizontal asymptote at y equals 0. Let's look at that graph. Here's our graph. So notice that there is definitely a line here you can't see because this eventually approaches it but never crosses it. Same with this. Okay, look at the second one. We have a polynomial on the bottom. We need to factor this polynomial. I can rewrite it as x plus 1 and x minus 1 and set each of those equal to 0. So I'll have two vertical asymptotes. And they're going to be at x equals 1 and at x equals negative 1. Notice that the degrees are the same. So when the degrees are equal, remember when n is equal to m, that means I'm going to take the coefficients that are in front of these numbers and put them and stack them. So the top is going to be 2, the bottom is a 1, so it's 2 over 1 or it's just 2. So at y equals 2 is my horizontal asymptote. Let's go look at that graph. Here we are. So asymptote at negative 1 and at 1, we also said there's a horizontal asymptote at 2. When we know these asymptotes and we can graph them, it makes the rest of the graphing so much easier because we can use those asymptotes as guidelines to give an estimate of where the rest of the graph is.